next lecture of quantum mechanics. In today's lecture, we are going to learn about the mathematical derivation of quantum tunneling, which is one of the most fascinating and surprising phenomenon in the quantum mechanics. So till now, we solved the Schrodinger equation for particle in 1D and particle in 2D, and from there we have calculated the wave function and the probability density of finding the particle in that particular space while substituting the corresponding boundary condition. So in today's lecture, we will again solve the Schrodinger equation and we will substitute the corresponding boundary condition to understand or to calculate the wave function in different region of finite potential barrier, and as well as at the end of the lecture you will be able to understand the transmission probability of finding the particle in the opposite side of the finite potential barrier. So this lecture will be the mathematical derivation of the quantum tunneling is large, so I'll break this lecture in two parts. So I'll try to calculate the wave function with constant in this lecture. In next lecture we'll substitute the boundary condition to calculate the constant for finding the transmission probability. So before diving into the mathematical details, first let's start understand this quantum tunneling with a physical example. So basically first try to understand what quantum tunneling is. So quantum tunneling basically explains you there is a finite probability of finding the particle in another part of potential barrier that classical mechanics does not predict. So let us understand these things with a physical example. So let's say if a ball is climbing over a hill, is that clear? If this ball is climbing over a hill and if the energy of this ball is E and the barrier height is, let's say, V0. So classical mechanics tells us that this ball will only climb and will appear in the other side of the hill when the E energy is greater than V0. But if the ball passes energy less than the potential barrier V0, then this ball cannot appear on the other side. So mathematically what you can see that if E is greater than V0, then the ball will cross the barrier. Ball will cross the barrier, right? And if E is less than V0, then ball won't cross barrier. And this is quite reasonable, and this is very this is perfect for macroscopic particle that has been explained by the classical physics or classical mechanics. But let's say if we talk about the electron, and if an electron is approaching a potential barrier, right? So let's say if an electron is approaching a potential barrier, right? So the barrier height is, let's say, V0, and if this is electron, right? And this electron is having energy E. Is that clear? So classical mechanics cannot predict that there is a finite probability of finding the electron in this particular region. So classical mechanics fails to explain that there will be a finite probability of finding this electron in this particular region. But what happens? The quantum mechanics tells that there will be a transmission probability of finding the electron in this particular region. And why is it possible? Whether the electron gains some energy from some external sources, or whether it is violating the conservation of energy. So this can be explained using the quantum mechanics. So in quantum mechanics, basically what happens, the quantum mechanics assumes that a particle behaves like a wave, and if a particle is behaving like a wave, then there will be a wave equation associated with it, or there will be a wave function. And the wave function is continuous, as I have already discussed this things in my previous lecture. And if this wave function is continuous, then this wave will basically penetrate this potential barrier. Is that clear? And the wave function will appear in this particular region as well. Is that clear? So let's try to understand these things, how these things appear in that particular region. So as I have told you that if this is a finite potential barrier, and if the electron is approaching this barrier, if this electron is approaching this barrier, that barrier, and if I am giving x equals to 0 and if x equals to a, is that clear? X equals to 0, x equals to a. So here in this region potential is 0, and in this region also potential is 0. Right. Now what you will see, there will be a wave, that will be an incident wave that is coming to this potential barrier, and since if we assume this potential barrier is very thin, then there will always a penetration of this wave in this potential barrier, and you will see this wave function will appear in the another side, and then there will be a wave that will be called as the reflected wave, something like that. So we call this as an incident wave. This is called as the reflected wave. And this is called as the transmitted wave. So this picture is very important when we will write the mathematical equation for that, because this wave will basically give you the boundary condition at x equals to 0 and at x equals to a. And you can see that when we will solve this mathematics of this particular problem, then you will see there will be two terms, one will be increasing and one will be decreasing. So if I am assuming this one is positive x direction, so here there are two waves which is approaching, one wave is approaching the finite potential barrier and another wave is getting reflected back, right? So this will increase the wave function and this will decrease the magnitude of the wave function, and here there is only wave which is going away, right? There is no wave which is coming in the negative direction. So if any wave which is going in a positive direction, we will assume as a positive, and if any wave which is going in a negative x direction, we will assume as a negative, and that will give you the boundary condition for solving the mathematics for that. Okay, so this is just about whether the wave is approaching a finite potential barrier and whether this wave is appearing in the other side of the finite potential barrier or not. Okay, so next what happens? So this quantum tunneling is not just a theoretical curiosity; it is having various physical examples in nature as well as technology. Like if we talk about the alpha decay in radioactive nuclei, or electron tunneling in semiconductor, or hydrogen transfer in heterogeneous catalytic reaction. And another example is also that enzymic there is hydrogen transfer in enzymatic catalytic reaction. So all of these places you will see there is a quantum tunneling. Okay, so now we'll start with the mathematical derivation of this quantum tunneling for a finite potential barrier V naught. As we have seen here, there is I'll divide this problem in three regions. This will be our first region, this will be our second region, and this will be our third region. Okay, so in this region we will assume the wave function will be your psi1. Here we will assume wave function will be psi2, and here we are going to assume our wave function is psi3. And in all these regions we are going to solve the Schrodinger equation, and after solving the Schrodinger equation we will calculate the value of psi1, psi2, psi3, and then we will calculate the transmission probability, and you will see what is the transmission probability for that particular problem. So let's start solving the Schrodinger equation first. So as we know, time independent Schrodinger equation. So time independent Schrodinger equation, if you write, it can be written as minus x squared by 2m d2 psi by dx squared plus v psi, that is equals to e psi. Is that clear? And then we can solve this equation for all these three different regions. So I'll divide these things. Let's say for region 1, what happens? The potential is 0, right? So if we write the boundary condition here first, so if we write the boundary condition, is that clear? So you can say that v equals to 0 when when x is less than 0, v is equals to v naught when 0 is less than equals to x is less than equals to a, and then again v equals to 0 when x is greater than 0. So we will use these three boundary conditions that basically tells you the region 1, that basically tells you the region 2, and this is for the region 3. Okay, so here we are solving this time independent Schrodinger equation for region 1. That's why I am going to
Actually, the third boundary condition is
x equals to a. Right. So here we are going to solve this Schrodinger time independent Schrodinger equation for region 1, where I will substitute the value of v that is equals to 0. So once you substitute the value of v equals to 0 in, let's say this is my equation first, what will happen? So we can write minus h square divided by 2m d2 psi by dx square plus v is 0, so it will be 0, and directly we can say that will be equal to E psi. Is that clear? So now if we rearrange these things, then you can write this equation like d2 psi by dx square plus 2m e by x square psi, that will be equals to 0. Is that clear? So here I assume this value 2m e by x square as, let's say, k1 square. Is that clear? So here you can see this is just a second order ordinary differential equation, and we can solve this equation very easily. So let's try to solve this equation. So as we have assumed that this equation can be written as now d2 psi by dx square plus k1 square psi, that is equals to 0, and the solution of this equation can be written as psi of x, that is equals to a e to the power iota k1x plus b e to the power minus iota k1x. So let's say I am assuming this equation is equation second, but what I have told you in region 1 I will assume the wave function as psi 1, so that's why this will be called as the psi 1. So till now we have calculated the value of psi 1, right? But this equation, in this equation you can see there are two constants a and b, and we can calculate this constant using the specific boundary condition. We will see these things later on. After that, here we will solve this Schrodinger equation for region 2, right? So let's say for region 2, v is equals to v naught. Is that clear? From the boundary condition. So once you substitute these things in this above equation, so it can be written as minus h square divided by 2m d2 psi by dx square plus v naught psi, that is equals to E psi. And now I rearrange this equation like d2 psi by dx square plus 2m 2m, here I write minus 2m b naught minus e divided by h square of psi, that will be equals to 0. After rearranging you can have this kind of thing. Is that clear? And then here let's say I assume this value, let's say this value is your k2. So I assume this is your k2 square. Is that clear? So finally I'll move this part here. Okay, and once we substitute this value over here, so you can write d2 psi by dx square minus k2 square psi, that is equals to 0. So from here we will be getting psi 2, that is the wave function in the second region, psi 2x, that is equals to c e to the power k2x plus b e to the power minus k2x. So here we have calculated the value of wave function in the region 2, and I'll assume this equation is our equation third, right? Now we'll solve the Schrodinger equation in region 3. Is that clear? So in region 3, what happens? Again, we have seen that in region 3, the potential was 0. If the potential is 0, then we can directly substitute these things like minus h square divided by 2m d2 psi by dx square equals to e psi, and this can be written as directly d2 psi by dx square, plus let's say 2me by h cut square psi, that is equals to 0. And if you see this value, we have assumed this 2me by h cut square as k1 square. So this is giving you the same value like this wave function, that is psi 1. Okay, so directly I'll write these things here, that the value of psi 3x, so the value of psi 3x we will be getting is e to the power, right, iota k1x plus f e to the power minus iota k1x. So I'll assume this is our equation 4. So till now we are able to derive the value of psi 1, psi 2 and psi 3 in all these three regions for the finite potential barrier. Now the next question is that how can we calculate the this constant A, B, C, D, E and F. So first here I'll start with the psi 3 because it's very important and where we can eliminate one constant, and then we'll talk about A, B and C and D. So as I have told you, in the finite potential barrier, if you see here, it was like that, okay, and here potential was V0 and there was a incident wave, then there was a reflected wave here, right, and this wave was going, this wave function was looking like that in this region and it is coming like that. So if I talk about this is our region 1, this is our region 2 and this is our region 3. So if you see here that in region 1 there is an incident wave and then there is a reflected wave, and due to this particular reason what is happening, you will see both of these parts will be there. One is incident and one is decaying and one is your increasing part, something like that. But in this region there will be only decay part. So there is this is positive x direction and we are assuming for positive x direction, if wave is moving in that direction, that will be increasing. And due to this particular region, what will happen? This negative part of this psi 3 wave function will be 0 because there is no wave along negative x direction. That's why this f has to be 0 to validate this condition. So finally, you will be left with psi 3x, that is equals to e to the power iota k1x. So till now we are able to eliminate one constant, that is f, from equation 4. Now we are left with only 5 constants A, B, C, D and E. So in the next lecture I'll substitute the boundary condition and we'll see how we can calculate the constant A, B, C, D and E. And at the end of the next lecture we'll be able to calculate the transmission probability of electron in the region, and that transmission probability we will define that is equal to magnitude of E by A, right? So we'll calculate these things and we'll see how we can calculate this. Okay, so thank you all for attending the lecture. See you in the next lecture. Stay tuned.